Good evening, everyone, and welcome to today's webinar. This is Sharat Nambia here, technical trainer at Upanal Education, and I'm very happy to have you all with us today. Our topic for today is SolidWorks Beyond 3D Modeling. When most people hear the word 3D modeling or SolidWorks, the first thing that comes to your mind is probably 3D modeling. We create a sketch, convert into the 3D model or a 3D part, and then that's where many people feel the software ends. But actually, 3D modeling is only one part of what SolidWorks can do. SolidWorks provides different tools and environments for different stages of engineering design and product development. We can work with individual components, sheet metal parts, complete assemblies, engineering drawings, complex surfaces, structural design, simulations and analysis, visualization, and even connect the design with manufacturing through CAM. So in this short webinar, we are not going to learn commands or perform detailed modeling exercises. Instead, our objective is much simpler. We are going to take a quick look at the different capabilities of the SolidWorks. Understand what each one is meant for, and most importantly, understand where and why it is used in the real engineering industry. By the end, I hope you will see SolidWorks not simply as a 3D modeling software, but as much broader engineering design platform. So before we explore different capabilities of SolidWorks, let us take a very quick look at where the software came from. SolidWorks was founded in 1993 with the idea of making 3D mechanical design more accessible and easier for engineers and designers to use. At that time, CAD was already being used extensively in industries. But 3D parametric modeling was still developing. SolidWorks focused on providing a practical Windows-based environment where engineers could create and modify 3D mechanical designs more easily. An important milestone came in 1997 when SolidWorks was acquired by Dassault Systems, the company behind other major engineering and design technologies. Over the years, SolidWorks grew far beyond the basic part modeling. More capabilities were added for assemblies, drawings, sheets, sheet metals, weldments, surfaces, simulations, visualization, and manufacturing. That brings us directly to the main topic of today's webinar. When we say SolidWorks beyond 3D modeling, we are really looking at how the software has evolved from 3D modeling tool into a much broader engineering design platform. And now let's look at the different capabilities one by one. Before we look into each capability individually, let us first get an overall picture of what we are going to cover today. When we talk about SolidWorks, we are not talking about just one type of modeling tool. The software provides different capabilities for different engineering requirements. We will start with the features and part modeling, which is where we create and modify individual 3D components. Then we look into sheet metal and weldments, which are useful for designing sheet metal components and structural frames. After that, we'll move into assembly and drawings. Assembly allows us to bring individual parts together to create a complete product, while drawings help us to communicate the design to manufacturing through dimensions and other technical information. We will also briefly look at the surface modeling and visualization, which become important when we are dealing with complex shapes or want to present a realistic representation of a product. Then we have simulations and motion analysis, where we can virtually study how a design behaves under different conditions or during movement. Finally, we look at CAM and manufacturing, where the digital design can be taken towards actual machining and production. So we won't be going deeply into any of these today. Our objective is simply to understand what each capability does and where it is useful. So let's start with the most fundamental capability of SolidWorks, which is features and part modeling. This is where we create individual components of a product. For example, if you are designing a machine, we may need to create a bracket, shaft, housing cover, gear, or any other individual component. Each of these can be created as a separate 3D part. First two. Start with a simple sketch and gradually build the required shape. We can add material, remove material, create holes, rounds, slots, and many other details until we arrive at the final component. One important advantage is that we don't have to create everything from scratch whenever a change is required, because SolidWorks use parametric and feature-based modeling. The designer can modify dimensions or features and the model can update accordingly. Think of it like building something using a set of intelligent building blocks. If the customer says, make the hole slightly larger, we can change the relevant dimension instead of completely rebuilding the components from scratch. This capability forms the foundation of most SolidWorks work. Once the individual parts are created, these parts can then be used in assemblies, drawings, simulations, and manufacturing workflows. So part modeling is essentially where our digital product begins. Next, we go to sheet metal. What do we do? Next, we have the assembly. In the assembly, what happens in assembly is we assemble multiple parts. That is multiple single parts into one component. So far, actually, we have created about talking individual components. But in the real world, products are rarely made from just one part. A machine, for example, may contain hundreds of or even thousands of individual components. Assembly in SolidWorks allows us to bring these separate parts together and create a complete digital representation of the product. We can define how the different components are positioned in relation to each other. For example, a shaft may need to rotate inside a bearing, a bolt needs to pass through a hole, or two plates may need to remain at a particular distance from each other. These relationships help software understand how the components should fit together. Another important advantage is that we can visually check how the different components interact. We can identify problems such as parts interfering with each other, incorrect positioning, or insufficient space before anything is manufactured. Imagine assembling a machine physically and discovering that two components collide. Correcting that problem at the manufacturing stage can communicate this design to the person who actually has to manufacture it. This is where engineering drawings become important. A 3D model gives us very good visual understanding of the component, but manufacturing often requires precise information such as dimensions, tolerances, material information, sections, and other technical details. SolidWorks allows us to create a 2D engineering drawing directly from our 3D part or assembly. The designer can generate different views of the components, such as front, top, or side. We can also create section views when we need to show internal details. The dimension and other manufacturing information can then be added to clearly communicate what has to be produced. So think of drawing as a technical language between the designer and the manufacturer. For example, if I design a bracket and send only a 3D model to a machinist, they can understand the general shape, but important manufacturing information may still be missing. A properly prepared engineering drawing removes that uncertainty. So the drawing capability helps us to convert our 3D design into clear manufacturing documentation. Next is this surface modeling. Surface modeling is nothing but we create complex shape using smooth and freeform forms. So what we do here, we mainly use this to develop the product surfaces like for the vehicle parts or all the exteriors or the aircraft things. All these things we'll be developing using the surface modeling. The next is the weldments. What is weldments? Weldments are mainly used when a product or a structure is made by joining different pieces of material together, usually through welding. Think about a simple industrial machine frame. Instead of manufacturing the entire frame as one solid piece, we may use CAD tubes, rectangular section channels, or other standard sectional profiles and weld them together. SolidWorks Weldments makes this type of design much easier. We can create the basic layout of the structure and then apply standard structural members to form the frame. The software can also help us manage how these members meet and how the overall structure is organized. So one particularly useful feature is the cut list. Instead of manually calculating every piece of material required for the frame, the software can identify the different structural members and their required lengths. This can be very useful during manufacturing because the designer and fabricator can understand what materials need to be cut and prepared. Weldments are commonly used for machine frames, workstations, platforms, support structures, equipment stands, and industrial fabrication. So if sheet metal is mainly concerned with designing components from sheet material, weldments focus more on building larger structures from structural members and joining them together. It is another example of SolidWorks being designed and around actual manufacturing requirement, not just creating testing before going directly to physical testing. For example, imagine we have designed a metal bracket that will carry a particular load. We can define the material, apply the expected load and constraint, and allow the software to calculate how the component may respond. The results can help us understand things such as stress, deformation, and factor of safety. The important point is that simulation doesn't simply give us a colorful picture. The results help engineers make better design decisions. If an area experiences excessive stress, the designer may decide to increase the thickness, change the geometry, and add a support or select different materials. This can help reduce the number of physical prototypes and identify potential design problems early. Of course, simulation is not a replacement for real-world testing, but this is very important. It gives designers a powerful way to evaluate a design before manufacturing it. The next capability is the motion analysis. We have already seen how simulation can help us to understand how a component behaves when the load is applied. Motion analysis looks at something different, how the components move. Many machines contain moving parts. Think about a gearbox, robotic arm, conveyor mechanism, linkage, or even a simple door hinge. The different components have to move in a controlled way and interact correctly with each other. With motion analysis, we can create a virtual representation of that moment and study how the components behave. For example, we may want to check whether a mechanism moves to the required range, whether two components collide during movement, or whether a particular component is moving too quickly or too slowly. We can also study things such as position, velocity, and acceleration, depending on the type of analysis being performed. This is useful because a mechanism that looks perfectly correct when it is stationary may still have a problem when it starts moving. Imagine designing a robotic arm where two links look correctly positioned in the assembly. When the arm actually moves, however, one link might collide with the other component. Finding that problem on the computer is much better than discovering it after manufacturing. So motion analysis helps engineers understand and validate movement before building the physical mechanism. Next, let's look at the rendering and visualization. When we create a normal CAD model, we are mainly concerned with the engineering side of the product. We want the correct dimensions, geometry, and functionality. But sometimes we also need to show people what the final product could actually look like. This is where rendering and visualization become useful. A CAD model can give realistic materials, colors, textures, lightings, environments to create a much more realistic representation of the product. For example, imagine that a company has designed a new machine enclosure. Before the product is physically manufactured, the company may want to show the management or a customer what the finished product could look like. Instead of manufacturing a prototype, just take photographs. We can create a realistic image from the digital model. Visualization is also useful during design reviews. Different colors, materials, or finishes can be shown to help people understand the proposed design. It can also support marketing, product presentations, catalogs, and customer approvals. So rendering is not necessarily about making design more beautiful just for the sake of appearance. It actually helps us communicate the design visually to people who may not understand technical drawings or CAD models. In simple terms, CAD tells us how the product is designed, while rendering helps us show how the product may look. Now we come to the capability that connects our digital design with the actual manufacturing, which is known as CAM. CAM stands for Computer Aided Manufacturing. Until this point, we have mainly been working with the design side. We created parts, assemblies, drawings, and even analyzed how the design might behave. But eventually, that design has to become a real physical component. For CNC machining, we need to tell the machine things like which tool to use, where the tool should move, how much material should be removed, and in what sequence the machining should happen. This is where CAM software becomes important. Tools such as SOLIDWORKS CAM and SolidCAM can use the CAD model as a starting point for planning machining operations. The programmer can define the machining setup, select suitable tools, and generate tool paths, which represents the movement of the cutting tool. The tool path can then be simulated to check the machining process before the program is sent for the CNC machine. Finally, the CAM system can generate the required NC or CNC program for the machine controller. The biggest advantages is the connection between design and manufacturing. Instead of manually recreating the geometry for machining, the CAM process can work directly from the digital CAD model. So we can think of the overall journey as CAD model, CAM, toolpath, CNC program, and physical component. And this is where our digital design finally becomes its journey into the real manufacturing world. So we have looked at various capabilities of SolidWorks, and I want to tell you take a moment to connect everything together. A product does not begin as a physical object sitting on the machine. It usually begins as an idea, which is then converted into an engineering design. With SolidWorks, we can create individual parts using features and part modeling. If the product contains sheet metal components or welded structures, we have dedicated tools for those requirements. We can then bring individual parts together using assemblies and create engineering drawings to communicate the design clearly. If the product has complex shapes, we can use surface modeling. If we need to understand how the design behaves under loads or movement, simulation and motion analysis can help. We can also create realistic visualizations to communicate what the final product may look like. Finally, through CAM, the digital design can move forward actual manufacturing. So when we look at all these capabilities together, SolidWorks is much more than simply a tool for making a 3D model. It can support different stages of engineering process from the initial design concept through documentation, validation, and preparation for manufacturing. And that is exactly what we meant by today's title, SolidWorks Beyond 3D Modeling. So before we conclude, let's take a quick look where SolidWorks is actually used. One of the reasons SolidWorks is so widely used is that its capability can support many different types of engineering and product development work. In mechanical and machine design, engineers can use it to develop machine components, mechanisms, equipment, and complete assemblies. In the automotive and transportation sector, it can be used for designing components, assemblies, brackets, housing, other product parts. Surface modeling can also become important when the product requires more complex shapes. SolidWorks is also used in consumer product design. Products such as appliances, electronic enclosures, tools, furniture components, and many other everyday products can be developed by using 3D CAD. Another major area is the manufacturing and engineering. The digital model can be used not only for design but also for drawings, design validation, and preparation of manufacturing through CAM. The important thing is to understand that SolidWorks is not limited to one particular industry. Wherever engineers need to design, document, analyze, communicate, or manufacture a physical product, CAD tools such as SolidWorks can become part of the workflow. So learning SolidWorks is not simply about learning software commands, it is about understanding how modern engineering products are designed and developed. So after seeing all the capabilities of applications, the next natural question, why should someone learn SolidWorks? The first reason is SolidWorks is a widely used engineering design platform. Learning it gives students, designers, and engineers a practical skill that can be applied to real product development. And the advantage is the wide range of applications. We have seen that SolidWorks is not limited to basic 3D part modeling. We can work with assemblies, sheet metal, weldments, drawings, surfaces, simulation, visualization, and manufacturing workflows. This also means that learning SolidWorks can open a different directions depending on a person's career interests. Someone may want to work as a CAD designer, while other person may be interested in mechanical design, product development, tooling, manufacturing or engineering analysis, etc. And the important point is the connection between design and manufacturing. When you understand how a component is designed and how it will eventually be manufactured, you become much more effective as an engineering professional. Of course, learning software alone does not make someone a complete engineer. We also need knowledge of engineering fundamentals, materials, manufacturing processes, drawings, and practical design. But SolidWorks can become a very valuable tool within that knowledge. So if you're beginning your journey in mechanical design or manufacturing, SolidWorks is certainly a skill worth exploring. We have now reached the main takeaway from today's webinar. If there is one thing I would like to remember, it is this. SolidWorks is much more than software for creating 3D models. We started with basic part modeling, where individual components are created using features. From there, we looked at sheet metals, weldments, assemblies, and engineering drawings. We then explored more specialized capabilities such as surface modeling, simulation, motion analysis, and visualization. And finally, we saw how CAD can connect from CAM and manufacturing, taking us from digital model towards an actual physical component. Of course, we only introduced these areas today. Each of them is large subject by itself, and learning them properly would require much more time and practical work. But the purpose of this webinar was not to make you experts in 1 hour. The purpose was to give you a bigger picture. When you hear the word SolidWorks in future, I hope you don't only think about creating a 3D shape. Think about the complete journey. Design it, assemble it, document it, analyze it, visualize it, and manufacture it. This is the idea behind SolidWorks Beyond 3D modeling. And once you understand this bigger picture, you can decide which area you would like to explore more deeply. So we have now reached the end of today's webinar. Thank you so much for joining me and spending a valuable time with us. I hope this session has helped you understand the SolidWorks is much more just than 3D modeling tool, and that you have a clearer picture of the different capabilities it offers across engineering and manufacturing. Before we close, I would also like to share an announcement for those who are interested in building practical skills in CNC programming and machining. Our batch 7 of the CNC Program Come Operator course is scheduled to start in the first week of September. This course is designed to provide practical knowledge of CNC programming and machine operations, helping learners understand the complete journey from engineering drawing and programming to actual CNC machine. So we have currently limited seats available for batch 7. So if you are someone who is interested in developing the skills, the CNC programming and operation, this would be a good time to get in good teachers and secure the seat. Once again, thank you all for being a part of today's webinar. This is P.R. Sharath Nampia, Technical Trainer to Upanal Education, and it was a pleasure having with you us. Thank you. Have a wonderful day, and please don't forget to follow, subscribe, and listen to other webinars we conduct each Saturday. Thank you all. Have a nice day.